Section 25.8, Standing Waves. If you tie a rope to a wall and shake the free end up and down, you will produce a wave in the rope. The wall is too rigid to shake, so the wave is reflected back along the rope to you. By shaking the rope just right, you can cause the incident, original, and reflected waves to form a standing wave. In a standing wave, certain parts of the rope, called the nodes, remain stationary. That means they don't wiggle up and down. Interestingly enough, you could hold your fingers on either side of the rope at a node, and the rope would not touch them. Other parts of the rope would make contact with your fingers. The positions on a standing wave with the largest amplitude are known as antinodes. Antinodes occur halfway between nodes. Here's a comment from Mr. H. The nodes are where no vibration occurs, and then the antinodes are the opposite, where the biggest vibration occurs. So let's look at the figure 25.13. So here's a rope swinging up and down, up and down, up and down, node. So here the rope goes way up high and then goes way down low. Over here it starts out low, goes way up high, so there's a lot of movement here. At the node, notice it doesn't go anywhere. It's right in the middle, right in the middle, right in the middle, right in the middle. It's not going anywhere. So where the mouse pointer is right now is a node where nothing is happening. Over here it's going way high, way low, way high, way low. And over here is another antinode. Way high, way low, way high, way low, and so on. Okay, so these are antinodes. Antinodes. Here in the middle is what we call a node. Standing waves are the result of interference. When two waves of equal amplitude and wavelength pass through each other in opposite directions, the waves are always out of phase at the nodes. Out of phase, opposite. One's up, one's down at the nodes. The nodes are stable regions of destructive interference. Destructive interference means they're opposites. One's trying to make their wave go up, one's trying to make it go down, and so what the result is nothing happens. The nodes don't move. You can produce a variety of standing waves by shaking the rope at different frequencies. The easiest standing wave to produce has one segment. If you keep increasing the frequency, you produce more interesting waves. Let's look at the figure 25.14. Shake the rope until you set up a standing wave of one segment. Looks like a jump rope. The rope length equals half of a wavelength. So look at my mouse pointer. I'm tracing out this standing wave that has one segment, one antinode, where it's going up and down like crazy in the middle. Looks like a jump rope. The entire rope is half of a wavelength. There's one crest, but look, there's no trough. A crest but no trough is half a wavelength. The center picture now, you're shaking it faster at twice the frequency. You produce a standing wave with two segments. So let's trace this one out. We have a crest and a trough. Trough and a crest. So that's a full wavelength. Okay, here's the node in the middle where it's not moving. Here's an antinode where it's going up and down a lot. Here's another antinode where it's going up and down a lot. This is another standing wave. Same rope, just different frequency. At a higher frequency we get this one. In the bottom picture, shake it even faster at higher frequency. So now we have three segments. Okay, we have a crest and a trough. That's one wavelength. And then we have another crest. That's another half a wavelength. So we have one wavelength plus half a wavelength. That is 1.5 wavelengths. So at this frequency we're getting 1.5 wavelengths in our standing wave. It's all the same rope, just higher frequency. Let's move on. Standing waves are set up in the strings of musical instruments that are plucked, bowed, or struck. They are set up in the air in an organ pipe and the air of a soda pop bottle when air is blown over the top. Standing waves can be produced in either transverse or longitudinal waves. Let's look at these questions. Question number 1. Is it possible for one wave to cancel another wave so that the combined amplitude is 0? Yes, it's possible. That's called destructive interference. Number 2. Suppose you set up a standing wave of 3 segments as shown in the figure. If you shake with twice the frequency, how many wave segments will occur in your new standing wave? And how many wavelengths will there be? Well, let's see. If you shake with twice the frequency, that means you're shaking faster. The wavelength gets shorter. We get more wave segments. So the wave segments get smaller, so more of them fit on the string. If we had 3 and now we're shaking at twice the frequency, I'm guessing we're going to go up to 6 segments. Let's go back to the picture. Here's a segment, a crest. Here's another segment, that's a trough. Another segment's a crest, that's 3. A crest and a trough make one wavelength, and then a crest makes another half a wavelength. So if we double that, we have 6 segments. Instead of 1.5 waves, now we have 3 waves, 3 wavelengths. So at twice the frequency, we would have 3 wavelengths fitting on the string.